Okay then, a little experiment. On the 2015 total eclipse, someone took footage off a plane of the total eclipse and it showed what looked like bubbles. So I've got a marble here that's similar to them bubbles. So let's see what happens. Let's see what happens when I shine laser pen through it. Alright, let's zoom in so we can see what's happening. Right, so sunlight hits the door, hits the bowl, and look what happens on the back door. What's that? A total eclipse. Total eclipse. And on a lunar eclipse, these bubbles would refract all the other light except the red light. And that's what gives the moon the red tint, because the red light gets through. It's not refracted. So there's your total eclipse and your lunar eclipse right there.
Absolutely amazing, and to describe it to you from, I mean, you can see it, but from the ground it almost looks.
Also, the phases of water. Now, we've all learned that there's a solid phase, a liquid phase, and a vapor phase. However, 100 years ago, there was some idea that there might be a fourth phase somewhere in between a solid and a liquid. Sir William Hardy, a famous physical chemist, 100 years ago exactly, professed that there was actually a fourth phase of water, and this water was kind of more ordered than other kinds of water, and in fact had a gel-like consistency. So the question arose to us, you know, all of this was forgotten because people began, as methods improved, to to begin to study molecules instead of ensembles of molecules. And people forgot about the collectivity of water molecules and began looking, the same as in biology, began looking at individual molecules and lost sight of the collection. So we thought, we're going to look at this because we had some idea that it's possible that this missing link, this fourth phase, might actually be the missing link so that we can understand the phenomena regarding water that we don't understand. So we started by looking somewhere between a solid and a liquid. And the first experiments that we did that get us going is we took a gel, that's the solid, and we put it next to water. And we added some particles to the water because we had the sense that something, the particles would show us something. And sure enough, you can see that what happened is that the particles began moving away from the interface between the gel and the water, and they just kept moving and moving and moving, and they wound up stopping at a distance that's, well, roughly the size of one of your hairs.
Is this why this image is so clear and then bubbles are so clear? Because all the particles have been moved from the EZ water, the fourth phase of water.
Now that may seem small, but by molecular dimensions, that's practically infinite. It's a huge dimension. So we began studying the properties of this zone, and we called it, for obvious reasons, the exclusion zone, because practically everything you'd put there would get excluded, would get expelled from the zone as it built up, or instead of exclusion zone, EZ for short. And so we found that the kinds of materials that would create or nucleate this kind of zone, not just gels, but we found that practically every water-loving or so-called hydrophilic surface could do exactly that, creating the EZ water. And as the EZ water builds, it would expel all the solutes or particles, whatever, into the bulk water. And we began learning about the properties, and we've spent now quite a few years looking at the properties. And so it looked something like this. You have a material next to water, and these sheets of EZ layers begin to build, and they build and build, and they just keep building up one by one. And so if you look at the structure of each one of these planes, you can see that it's a honeycomb, hexagonal kind of structure, a bit like ice, but not ice. And if you look at it carefully, you can see the molecular structure. So of course it consists of hydrogen and oxygen because it's built from water. But actually, they're not water molecules. If you start counting the number of hydrogens and the number of oxygens, it turns out that it's not H2O. It's actually H3O2. So it is possible that there's water that's not H2O, some phase of water. Say this is a lizard from Central America, and because it walks on water, it's called the Jesus Christ lizard. And of course, you'll say, well, I know the answer to this. The surface tension is high on water, but the common idea of surface tension is that there's a single molecular layer of water at the top, and this single molecular layer is sufficient to create enough tension to hold whatever you put there. I think this is an example that doesn't fit that. And here's another example. 2 beakers of water, you put 2 electrodes in, and you put a high voltage between them, and then what happens is a bridge forms, and this bridge is made of water, a bridge of water, and this bridge can be sustained as you move one beaker away from the other beaker as much as 4 centimeters, sustained essentially indefinitely. How come we don't understand this? So we began looking, of course, more into these extremely interesting properties. And what we found is we stuck electrodes into the EZ water because we thought there might be some electrical potential. It turned out that there's lots of negative charge in that zone. And we used some dyes to seek positive charge, and we found that in the bulk water zone, there was an equal amount of positivity. So what's going on, it looked like, is that next to these interfaces, the water molecule was somehow splitting up into a negative part and a positive part. And the negative part sat right next to the water-loving material, and the positive charges went out.
So this EZ water is highly negatively charged. So if a blob came off there, because there's no atmosphere at the top near it, it would fall at great speed. And when it got to a bit thick of atmosphere, which is positively charged, it would slam into the positive energy atmosphere. You get a positive and negative together, you get plasma. So if a blob came off, it would fall at speed, slam into the positive atmosphere, and you would get a ball of plasma, shooting stars and meteorites, which it would answer that. So that's another supporting evidence that the firmament is a full phase of water.
I know we have still not shattered that highest and hardest glass ceiling, but someday someone will, and hopefully sooner than we might think right now. I can't believe we just put the biggest crack in that glass ceiling yet.
Compound in the whole world. 99 out of every 100 molecules is this one. And water is the major thing on everything on this planet, and that should be the ultimate focus of place where we can clean up and make a significant impact. But now let's talk about those chemtrails which spray out and then diffuse out. And by the fact that I was in the movie What in the World Are They Spraying with Michael Murphy back about 6-7 years ago, I became noted as the resident expert. And the three things we're really worried about are barium, strontium, and aluminum. And actually, the form that they are in the sprays are as the oxides. So we have barium oxide, strontium oxide, aluminum oxide, but notice aluminum oxide is Al2O3. And that's because the aluminum with its 3+ charge has to be balanced to the oxygen with its -2 charge. And so to get these balanced, that's why we need 2 aluminums and 3 oxygens. And this is called alumina, and that's one of the major components of what they're spraying. So why are these 3 the big bad guys? Let's talk about barium and strontium first. Now, actually, let's talk about barium and strontium first. Let's blow up this part of the periodic table that we had. And here you have sodium and potassium, lithium. You get barium and strontium down here. And so these are +1 guys, and these are +2 guys. Well, above the barium and strontium are things like calcium and magnesium. Now, we know that calcium and magnesium are very important to biological systems. And it turns out that the way the periodic table works is that when you're high in the periodic table towards the top of it, you're talking about small molecules, and as you get down lower, you're talking about bigger and bigger molecules. So lithium's a nice small molecule, sodium's a little bigger, potassium's bigger, and these all have 1+ charge. When you get to magnesium, magnesium with a 2+ charge is actually a little smaller. Well, you know what? Magnesium's on the wrong row because it's actually supposed to be on sodium's row. But it's 2+ charge. Magnesium is a smaller ion than sodium because being right next to the periodic table, you've got positive charges in the middle and electrons that are negative charges around the end. And to get these positive charges, you release electrons. If you've got 2+ charges, all the rest of the electrons are pulled tighter into that nucleus. So even though you think this is bigger, it's not, it's really smaller. And so what happens when they spray is that in biological systems, well, what's a biological system anyway? Everybody has a, okay?
I'm one.
In fact, every biological system is different, but it's usually made up of the same stuff. And the major component of a biological system is water. But copacetic. Now, magnesium is fairly small. Calcium is about the same size as potassium. Strontium is a little bigger than calcium, and barium is a little bigger than strontium. But you see, if we were to substitute a strontium in for this magnesium, and you know, that's what I think we're doing with the chemtrails, so we put strontium in it. Now, this is a bigger atom than was in it with the atom that belonged. And so, because of that, that's going to push this out of whack. This is going to have to be back here, and it's going to start breaking bonds and causing chemistry because you're putting a big molecule in place of something that was smaller, and everything has to spread out to accommodate it. The barium is even bigger than the strontium, and so now you can see when you get a barium into the lattice, first, it displaces a whole lot of things in the lattice. Second, it hangs on better so that you can't get it out of the lattice once it's there. So as where normal chemistry might have calcium substituting in for another calcium, and that'll work for a little while, and then another calcium will come in. Once a strontium or a barium comes into a porphyrin ring, it gets stuck. Now, yes?
Why are those getting substituted? What is it that's allowing? I mean, we're surrounded with all kinds of metals and chemicals all the time. Why are those getting sucked into the ring? Why is
this is an example of how the specific mechanism of a ring was only chosen because it's convenient to talk about. We could easily substitute it onto this molecule down here, in which case we'd have a calcium which is a lot bigger than a sodium, but here at least it's on the end of the molecule and can get swept off. The real problem with it is that, as I said, these things form as oxides, and they're stable in their charged form as oxides, and so when they stick to an oxygen, they think they're in their normal inorganic place. They're not really ready to go leaving the site they're at, and that's what holds them in, is the fact that the bigger molecules have a more finite attraction for the site than the smaller molecules do, and so the smaller molecules can't knock a bigger one out. Eventually that does happen.
Is that gravity?
Not necessarily. I think it a lot has to do with the size of the fit and the cavity that it's in and how much distortion it caused in a molecule. Because if you twist a molecule and it really is out of shape, the forces to put it back into shape are going to kick that off. But if you just make a subtle change and you make everything loose, what happens is that the components that get loose don't function as reliably And so your mechanism for doing something like breathing and intaking oxygen might slow down because you've got things cluttering some of your sites because they wouldn't let loose like the molecule was supposed to.
I'm no expert in chemistry, but what I was picking up from this talk was the changing of a smaller atom for a bigger atom will distort the structure, making it weaker.
Yeah, a lot of this spraying started back after World War II, and the nominal thing is that it is a way of protecting the albedo of the Earth. That by spraying these geoengineered chemicals in the sky, somehow it's going to increase the reflectivity of the Earth, and so much heat won't come in and that. I don't know that I believe that explanation, but that's what they've been giving us. And it's a little strange. I tend to think that maybe what they're spraying is magnetic chaff, and that they want to change the vibrational frequencies that are out, because if it seems like this planet has a poisonous atmosphere, maybe the aliens will attack us. I don't know.